go and again if the question is repeating, that is not a big deal. Just go there, ask doubt. That's all. And if you see that, that's why if purposely we keep like this session each day. You have a session, even Sunday, Monday. If there is no instructor session, then there is a TA session. So Sunday, Monday, Tuesday to till Saturday we have. So like each day if you have, then if you are getting any doubt, okay, any kind of doubt if you are getting, then go to TA session. You can come to instructor session. Like yesterday you come to, today you have any time a session, probably at evening, or today at Saturday we have in morning.
I understand that, sir. But sometimes we will come to know some other technique for doing the same question when we attend the session. But if you are not able to attend the session on a particular day, if there is, at least for some days, if it is in the YouTube, and then you can remove it after a week or so, then for those people who are not able to join, can view it.
So yeah, for this purpose, that's why the instructor session is we usually keep on live. TA session is just for doubt only, just for doubt. That the instructor session, we used to discuss the concepts also. So if you have doubt, you want to, like, if you have remember any problem, you want to ask any different approach, so you can ask in any one of the instructor session. We can discuss that. If we started doing live, no, so each day we have to do live each day. So that's the issue we'll get.
We can remove this. It is my request, sir. We can remove that video after 2 weeks or 3 weeks, no, sir. So that
We can remove that. Okay. But I don't know. I don't know why it is so. Like each day we have, it is a kind of, if you are getting any doubt, just go to the next session and ask, can you discuss the different approach? That's all. If any doubt, can you ask? And that's all. So that's your issue, that you have to record that. If you are forgetting, you have to clearly listen. And again, you are getting doubt, just come to the next session and ask again that. That's the purpose. That's why we used to keep this much sessions per day sessions.
Yeah, I really appreciate there are many sessions. Okay.
Until recording or keeping is not always easy, no? So like this one is also on streaming, so it is not always like somebody is there to do on live. Some other person is there. So similarly for TA, we have to fix a person and to do live. Like this, there is a issue. So that's
Oh,
why
okay.
But they can,
some sessions will be live and some sessions we are just as it is will go. If you have doubt, just ask. That's all.
but sir, like the previous year question sessions last happened in Q1,
Yes,
right?
yes.
Like that.
This also. Then the next week will continue with the
Yeah,
previous
like that also. Last time what they did is they recorded it and then pasted
it
that
will be
YouTube,
similar. Yes, yes. It
pasted
will be
that
similar.
link in the meeting information itself.
Yes, yes, yes.
Can they
In the
do
calendar.
the same thing here
Yes,
also?
same way will go. Same way will go. Whatever the importance of session we have, we used to record that. Streaming is not possible in for the TA session. Recording is always possible. Most of the time, the TA can record and then have to give the link there in the calendar. So PYQ sessions will be like that. Okay. So let's start the session. This is Maths 1 session for week 9. Let's discuss. If anyone have doubt, please let me know. Otherwise, I will do a conceptual summary. Yes.
9.4 activity, sir. Question number 6.
Okay.
So before that, can you do a conceptual summary?
Okay. Yeah, you can do the conceptual also, and then in the end I will ask.
Because there is no summary video available this week. I mean, I was trying to find one.
Yes. Okay.
I will ask the doubt towards the end. Please.
Okay. Which activity?
But he wanted a summary video, sir. So summary
Okay.
after that.
So in week 9, last time Vishal have taken, I hope last to last I took and discussed the till differentiability I have discussed. And yeah, tangent and linear approximation, I hope Vishal have discussed those all. And L'Hopital rule also remain, yeah. That L'Hopital rule, I hope he had discussed also. So it is a continue, no? Calculus, whatever the 3 weeks we have, it is a continuing. So critical point is also a part of differentiability. So I hope all of you have, where is that? Okay, so my voice is clear, right?
Yes, sir.
Yeah, sir, your voice is clear.
Okay, so uh, uh, that critical, differentiability definition is clear, right? To all of you, that what is the differentiability, or even how to find the derivatives of a function. Suppose you have a function from real number to real number, or maybe some subset of real number or anything. If you have such kind of function with this thing is happening, suppose A is a element from the domain, this is a domain R, and if you take if the function have this property that if you try to evaluate the limit at A, okay, with the differences and the ratio form, like just do increment in the function, and whatever the increment we have did, divide with the increment of the input, so which is such here. And if this limit exists, then we will say function is differentiable. And some particular, like so this is the checking, or this is say if limit exists, then that's all we will say that function is differentiable. But the derivative thing is that, means if you have a function, suppose fx is equal to, I'm just writing the form of polynomial. Okay, if you have this function, so it is very obvious that this is a polynomial, so easy to check. Even not each is we have some formula that if you have a function, or even if you have x to the power n, if you derivate this, this will be n x to the power n minus 1. So this is the derivative of this one. This is a derivative of this one. So if you can use this formula to find the derivative of the function, it is very obvious. Actually the all polynomials are differentiable. There is that those are actually infinitely many times differentiable. Polynomials are generally called very smooth function. So smooth means a function, if it is differentiable infinitely many times, we will say that function is a smooth generally. So here is polynomials have such property, and if we will try to find the derivative of this function, which is going to be the same term, each term we will try to apply this formula. So this is going to be 5x to the power 4, and this is 6x, and this is 0, it will be. So finally this is the derivative we will get here. So first thing, this is the derivative. So what is the use of this derivative? Why you will try to find the derivative of such function? So one use is finding the tangent, right? Tangent line. And the second is linear approximation. It is also used to approximate. If you don't know uh, uh, what is the approximation, suppose if you have a function and you don't know at this area, there is some information is missing, and then again you know the graph of a function at least. So this is a x-axis. So at least in this area you don't know what is the how the function is behaving. It is like this, or it could be like this. We don't know that. So if this area is missing, so we'll try to approximate, and the approximating that we should needed information. Suppose here is alpha, some alpha at here, you know the derivative of the function f. f prime alpha. Some value is given. Okay, some value is given. We will use this value and try to approximate, or even we can use this one also, wherever in the point also we can use to approximate that. So approximating means here we will try to linearly approximate, like a line. Exactly, we will try to match these 2 points like a line. This is the meaning of linear approximation. So this is another use of differentiability or derivative of a function. And third thing is we'll try to find the maxima or minima of the function. And another use we can say that here is that to check a function is increasing or decreasing. And that is, if you just derivate that, okay, you derivated that, and in some particular interval, okay, some a to b interval, this derivative is always positive in this interval. So in that case, the function is increasing. You can check with the x square function. Okay, if you derivate, this is going to be 2x, and if you check this interval 1 to 2, this is always positive in that interval. So that means in this interval, function is increasing. And if it is less than 0, then it is decreasing. So this is, there are 4 applications we can see here. This one, tangent, linear approximation, to check increasing and decreasing. And fourth is maxima minima. Maxima minima. So how we can find this maxima minima? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir. You're right.
Okay. And please stop me if anything if anything is not clear to you. Okay.
Okay, sir.
So, so to find this maxima minima, we needed not only the derivative of a function, second order derivative also we needed. That is called test. We will use that second derivative to test that function is at that point is it give the maxima or minima. So what is the second derivative? So if you have, suppose, a function 5x, okay, simply I am taking this one, and if you are derivating this one, so derivative of this is going to be 5x to the power 4. And again, if you derivate, okay, if you derivate, this is the sign of prime, means I am derivating this function. That means here x to the power 5, okay, double derivative, means 2 dash. This is a dash sign, means derivating twice. So if you derivate this function, this is going to be, if you again derivate this one, okay, so means here, this one, and this is going to be 5 into 4 x cube, which is 20x cube. So this is the second derivative of this function. Okay, this is the second derivative of this function. So the same way as you are doing the first derivative, it is exactly you have a function derivated function, and again you will try to derivate that. So that means you have derivated this function. So second derivative is going to be limit h goes to 0 f prime and increment that f prime value at that point upon h and limit value at that. So this is the second derivative, exactly as here we are doing. Derivate first time, again derivate that derivated function, again derivate that is going to be second derivative. So we will use this second derivative to check at which point function has maxima or minima. So there is a connection between the first derivative, and we will use the first derivative, and then we'll use the second derivative to find the maxima and minima of a function. So maxima and minima of a function, we can think with the different real life example. Like if you have, this No, suppose simply you can think like if you have a field which is a circle shape, okay, and you want to fence a area of the circle which is in the rectangular form. Okay, you want to fence a area in this field in the form of rectangle. Okay, and we will try to find the maximum possible area in the rectangle. How we can maximize this area? So how can we can get this? How we can get this length and width of the rectangle? So this is one application. We can change our problem in the real life problem. Okay, this is the constraints we have, that we cannot go beyond of this circle. Okay, and within the circle we'll try to maximize our area. So this is one real life example of maximizing, or what is how to find the maximum minimum of function. So you can see this one. We can convert this our problem in the mathematically. So suppose you have this, no, suppose you have a this circle, so which is of a fix. This is a fix. You have a fix circle field. This field of a fix in this range under this circle. So which is if you know area, so which is pi r square, or perimeter. So probably you will know at least the area, which is pi r square. And now you know the formula for finding the area of rectangle. So suppose this is x and this is y. So area of rectangle is going to be x is equal to y. Now using these two equations, we will to convert this x, and we will using these two we will convert this function in one variable. This is in two variable, no, x and y. So we'll try to change this problem in one variable, and we want to find the maximum area, no. So that means we have this function. We'll try to convert this function in the one variable, and we'll try to find the maximum or minimum value of this function. So suppose how we can convert this problem. So we can think at the center here, and this radius we know that. Okay, we have this radius. Okay, we have this radius. So uh, mm, we have this radius, which is pi r square. It is given. Sorry, area. This r is fixed. So let's say so this is, suppose r is given. Now we'll try to connect with the x and y. So we have to think something, so that we'll try to manage, or we'll try to bring in one variable. So how we can do this? So this is this is also going to be x, and this is x. Sorry, this is r radius and this is r radius. Surely it is a maximum. We'll try to find the maximize that. That means it will surely touch the boundary. Okay, or even the problem could be asked, touching the R4 corner will touch the boundary. So this is we have. So if we know in this form, maximizing under this circle is how we can convert this problem. Even I think some extra information is needed. That is, or we can say the whatever the perimeter of this circle, okay, which is 2 pi r, is going to be exactly the perimeter of this within the constraint. We'll try to convert that. This is the so I'm changing here, and this is the information we have. The perimeter of this circle is given, okay, and whatever the perimeter of this circle is given, that is going to be the exactly perimeter of the rectangle. So that is so this is 2x and y. So this is the perimeter of rectangle. Okay, now anyhow so this is going to be pi r, and x or y equal to, which is we can write y equal to pi r minus x. Now see that. So r we can think, suppose the perimeter is given as r is given as a 5. Okay, so which is 10 pi is given, so we can write like this is going to be 5 pi. So 5 pi. Suppose the r, which is radius of the circle, is given 5 meter or 5, whatever, in 5 meters, suppose it is given. So now see that I use this one and I converted this y in the fix whatever the constraints we have given, and then we have I want to maximize this function. No, this is the area of a rectangle. So we can think this is the function which is ax, area, axy kind of, you can think axy, which is here going to be xy. This is the area function. Now this is in two variable, we know only one variable. Using that, we will try to maximize this. So this is going to be area, and x and y could be written as a 5 minus x. So this is exactly going to be 5 pi is here, 5 pi minus x. Now see so this is not, this is x here. So this is 5 pi x minus x square. Now our area function is exactly the function of x. Now it is in the one variable, and now we'll try to find the maximum or minimum of this one, and we'll get that. Okay, what is the maximum possible area in this circle? So now it is touching the circle or not, we don't know. We have the information that whatever the perimeter of this rectangle we have, this is exactly the perimeter of the circle. So we want a area within the circle which have the exact perimeter as the circle have. So using this function, we'll try to maximize that maximum value. We'll try to find that, and x value will get, similarly y value will get. And so we have this function. So how we can use now here the differentiability, we'll see now. Okay, so this is one example, real life example, that we don't know how we can maximize it, but using, or even you can, if you are able to gauge the perimeter of the circle, and then within that we can get a rectangular area, maximum possible rectangular area, by using the calculus. So this is not only one, there are so many applications. So to reach this maximum, how we'll get? So there is one way, which is there is one concept which is a critical point. Okay, as the name is given, also critical means critical, which is at these points there is a possibility which is related to the function, that function is, if the function is differentiable, okay, or even if the function is differentiable in interval, then at that point the derivative of the function is going to be 0. That means if you suppose you have a function, okay, and you are saying a is a critical point, okay. So if you derivate, or if you find the derivative value at a, which is, so if you are saying a is a critical point, then it is going to be 0. Or the second thing is that at that point, suppose again you are saying a is a point where the function is not differentiable, that is also going to be a critical point. So there are two things you can say. If the function is differentiable, or differentiable and derivative is going to be 0 at that point, then it is a critical point. Or at that point the function is not differentiable, then that is also a critical point. Okay, so generally if we know that if the function is not differentiable at some particular point, we will use that critical point, and where the derivative is going to be 0, we will use that point as a critical point. So simply, so our area problem is again here, ax is equal to 5 pi x minus x square. So this is a problem we have, this is function. So we want to try to find the critical point. So we just need to observe that this is a polynomial, no? So we can directly derivate. So this is infinitely many time differentiable, or you can say everywhere it is differentiable. So there is no point to discuss that. that a function is not differentiable at a particular point. So only this will work. Okay, this will work to find the derivative. That just find the derivative and equate them equal to 0 and find the value of x. So if you try to derivate this one, so which is going to be a prime x. So this is going to be 5 pi minus 2x. So this is the derivative of the function. Now just equate to 0 and we'll try to find the x value. So the x value is going to be 5 pi by 2. So at here, the derivative of the function is, this point is actually a critical point. This point is a critical point for the function this. Okay. So we'll use this one. Okay. So similarly, so here is, this is one linear function. So only one root is there for this equation. There may be possibility that there are, it could be of more than 1 degree, which is 2 degree, 3 degree, 4 degree, or even sometimes at some places function is not even differentiable. Even we can think with the stepwise function. We can think such function, suppose fx is equal to, okay, I'm writing like 3x square minus 5. This is behaving when x is less than 0, and 5x to the power 4 minus 3x square plus 2. It is behaving when it is greater than 0 but less than 5. And again in the next step, when x is greater than 5, okay, it is behaving like sine. So this is one function. Okay, this is one function. So at 0, at 5, we have some problem. We will check that at this point function is differentiable or not. If it is not, then 0 and 5 will be counted. So 0 and 5 will be counted as a critical point. If it is not differentiable, except there is 2 points, we'll try to count the critical point here, here, and for here, this one. So can you tell me how many critical points? Anyone can unmute and tell how many critical points for this function have? Am I audible?
Yes, sir.
So can you tell me, or anyone, how many critical points? While looking itself, we can tell. Can you tell me? This is easy to say. How many critical points we have?
Except for the first function, like
For the whole function, for this function, the fx.
fx for the whole.
I'm asking for whole, not even in the steps.
0 and 5.
We didn't check, no. So I don't know. We have to check that as 0 is going to be a differentiable or not. But I'm just asking. So in this answer, you can answer this one in the word finite and infinite. So I'm asking in that words, like it have a finite critical point or it have infinitely many critical points.
Finite.
Why you are saying it is have finite?
Oh, yeah. So I was thinking that we can actually differentiate and see if it is a critical point.
So okay, that is one thing. Without, if you see only just why observation, without, it is not needed. No, just one information is needed, that if you know the property of sine, that's enough to tell that it have finite critical point or infinite critical point. So I'm asking that sine function you have, and okay, and sine function have finitely many critical points or infinitely many critical points.
So it actually goes on, right? Every pi by 2, it will actually.
Yeah. So
It's infinite.
So it have infinitely many, right?
Yeah.
Same. I used this one, and I also said that I want answer in the two terms, finite or infinite. So we have already, we can see that this sign is there. So I don't know. It have maybe, so surely it will give at least one critical point, because this is a 2 degree, and this have some, I don't know how many, but we can get that at least. To try to derivate this one, it have a 3 degree polynomial, and 3 degree polynomial have at most 3 roots, so it could have 3 So this has become 1 and this is 3, but sine have infinitely many, right? At sine function, if you try to see the graph, we have already very much familiar now, I hope. So this
Yes,
is
sir.
going to be like this, right? So at these points, these are the maximum points. So at here pi by 2 is going to be maximum. So similarly, this is going to be 3 pi by 2. So rest all like this, it will go. More than that it will go. I don't know, it is going to be 5 pi by 2. Here is 1. So there are infinitely many critical points possible for sin x. So yeah, I think I did not give much information. So another information regarding the critical point is that suppose if you have a graph of a function, okay, and if you know that like this, a graph of function is given. So at these points where the tangent is exactly going to be parallel to x-axis. So with the graph, you can tell the local maxima and minima. So maxima and minima in the sense of that local maxima and minima we are going to talk about. So there is another word, global maxima and minima. So that is the different thing. So in some particular interval, we generally ask the global, or even question will be asked in the global maxima and minima. But here is the concept of maxima minima means local maxima and minima. So where if you see the tangent where it is, if you try to draw that the highest or peak point, it will be exactly parallel to x-axis. So those point is going to be the maxima minima, and here if you corresponding point on the x-axis mean domain point is going to be a critical point. So these points are actually critical point. So similarly for the sine, these points are maximum value. So by this way you can tell that it have infinitely many critical points. So this is one geometric geometric observation to say that where is it is going to be critical point. So for example, I'm making a graph of function, okay. So suppose like this is there, and then this sharp corner is there, and there is a gap is there, these two sharp corners are there, these are the local. So at sharp corner, so at sharp corner function is not differentiable. So this is going to be critical point. This is going to be critical point. Here is one, uh, local maxima, and I'm making another thing that, S kind of shape is there again. So at S kind of shape, and the function is there is not differentiable. So that is going to be also a critical point. So these are the critical points where the function have the sharp corner is going to be critical point. Local maximum point is going to be critical point. So these all are actually the critical points. So let me change that. So these are the point where, so see that it is a kind of, jump is there. And then it is decreases, then again increases. So these are the critical points we have. So here is the
But
sharp corner.
slope is going to be parallel to the x-axis, right?
Yes. Slope is going to be parallel to x-axis. That is one critical point, or function is not differentiable. So this point, yeah, so I missed that. This point is here, the function is not even continuous. So how it could be differentiable? So this point is going to be a critical point. So these are the points. Here is a sharp corner, here is a soft corner. So these points are at this point, function is not differentiable. So this is going to be a critical point. This is a critical point. This is a critical point for the local minima. Here is the, S kind of shape is there, if you try to get that, or even you can know the tangent is exactly parallel to y-axis. So at that point, if you try to derivate that, the derivative or even a limit is going to be infinite. So in that sense, you will say function is not differentiable. So here is also it is going to be a critical point. So this critical point is generally known as the saddle point. Okay, there is 3 type of point: local maximum, local minima. Okay, the critical points have 3 definitions. So this is also a critical point, but it has a particular name. I will write that name. So this is also a critical point, and now rest all. Now if I will ask that, okay. So till here I made this, and then I am just ending now. And this is our interval A to B. So in visualize form, let's discuss that. Okay. So this is a local maxima. Sorry, this is a critical point. Okay. Now I will ask, what is the global? Okay. What is the global maxima? So global maxima is, what is that global maxima? So these are the local maxima. Okay, these are the local critical points. So at critical point, have surely see that this where function is not differentiable. Here is also a critical point. No, this is also a critical point, and it have the local minima. So this is one local minima. This is a local maxima. This is a local minima. So here is the minimum. Local minima means your value is actually decreasing, and from a fixed point it started increasing. So that fixed point is called local minima. Okay, that's the meaning here. What is the meaning of even, you can know, the name itself is telling that function is here continuously decreasing, and from the fixed point it is started increasing. And similarly here, this is a local maxima. Okay, this is a local maxima. So here is increasing here till here it is increases, but there is sharp corner and back is started losing his values and means decreasing. So the maximum peak point, at least in the local form, this is called a local maxima. Again decreasing, and again sudden started increasing. So this is a local minima. And again here is increasing, decreasing, the same way it is going. So these are the local maxima and local minima. So these critical point. So global is going to be the global maxima is going to be here, this one. This is going to be the global maxima, as this value, if you compare the value, okay, at least, okay, this is going to be like this. So if you compare these, see the corresponding points are these arrow. So this is the maximum value in compare of all, at least from 0 to whatever the range between, at the range I said between A to B, in this range the global maxima is here only, and local, so and global minima is this is the point which have the minimum value. No, global minima is in some interval we want. So global means we want that value at where it have, in that interval it have minimum value. So global could be, right, the minimum value is going to be, so here is, suppose I'm making this is going to be much smaller, like this. I'm just backing here now, and or even this is the started now. So this is going to be global minima in compare of all others. If you check that, this is going to be a minimum value in compare of all other local minimum values. So this is a global minima. So in this interval A to B, this is going to be global minima, and this is going to be global maxima. And these are the local maxima and minima is there. Okay. Now we have three type of critical point. Okay. Critical point, we have three type of critical point. One is called for local maxima. Okay. And another is for local minima, and one is a saddle point. Another critical point is generally known as a saddle point. So like here, this yes shape. So this yes kind of shape is not, it is look like it is there is a fluctuation. It's look like, there is a turn happening from increasing to decreasing, increasing, but it is not. While looking this in apparent form, it is look like there is a fluctuation. There is a increasing to decreasing is happening, but it is not. It is actually increasing. It is continuously increasing, but there is a fluctuation. So fluctuation is what? At that point, function is not differentiable. Meaning is that the limit, if you try to evaluate this limit, that limit h goes to 0, f of a plus h minus, even this is suppose this is a delta. So at delta, so delta plus h minus f of delta upon h. Okay, at here at delta, exactly delta, it is going to be, this limit is going to be infinite. So this is one point where it have saddle point.
Saddle point also when it is like horizontal, when it is 0. Correct.
So that is a horizontal, no? Horizontal, no? It will, if you try to, at that point, if you try to get the tangent, it is going to be exactly vertical, parallel to y-axis. So saddle points are those points where if you try to get the tangent, at that point tangent is going to be vertical or exactly parallel
But
to y.
so what about y is equal to x cube, right? So that will be like one passing from x-axis to it will be crossing the x-axis and there won't be any local maxima or minima, right? So that will be a saddle point.
Okay, yes, this here is also going to be, so this is going to be, so here is one. So this if you try to, yeah, here is the tangent is exactly the x-axis, but yeah, this is a fluctuation is happening, yeah. So not only the tangent or, exactly parallel to, the vertical also is going to be this one. And this is also, yes, this is one extra thing that I missed that. So this is going to be a saddle point here at x cube. There is a fluctuation, it look like fluctuation is happening. Sorry, there is an increment increasing to decreasing or decreasing to increasing is happening. But if you get that, it is not.
So in that sense, that jump points are also saddle points.
Jump point.
Yeah, in the left hand side, that breakage where in the graph, yeah, the
No, it is, so it is not a saddle, no, it is not saddle, it is a, local maxima.
okay.
It is a
Local
maxima,
maximum.
right? This side is your decreasing continuously. Here is decreasing, and at the sudden it started increasing with the jump.
Okay. Why it is not local minima? Because it is a dip, right?
This one.
The one you have marked as local maximum. Now.
This one here you are saying.
Yeah,
Sorry.
the just the one we talked right now. Yeah, the jump area only. So because it
So
is
here
kind
is
of dipping.
not maxima. Sorry, local minima. Reason is it is decreasing, continuously decreasing, and there is a exactly jump and it started now again.
Okay. I was actually trying to figure out like it's not exactly like 90-degree, but it's kind of on the side. So
Yes,
it doesn't have any kind of what is that?
you are saying in this way it is. Suppose this this one, and then like this.
Yeah.
Okay. So decreasing, and there is increment is there, and then again decreasing. So what we will say about this point? Is this local maxima, local minima, or what is this?
Yeah, that particular point is local minima, right? And the top point on top of that is the local maximum.
No, but how it could be? Again, it is a local maxima, no?
Okay.
Slightly change as here. This is this in compare of if you what is the so that's the here okay, so that's the here definition is that local minima is what? If you take around the interval, suppose this corresponding point is here, okay. So if you around this interval, that is a neighborhood you call. In the neighborhood, it is going to be if you compare the other values with exact that point. If it is a minimum value, then it have local minima. And if you compare with the other values, it is going to be greater than that. Then it is going to be local maxima. That's the definition you will give. What is the definition of local minima and local maxima? Just take a small neighborhood of that point. Around that, find the values and compare with the exact where you are getting maximum minima. So if you compare at here, you have maximum value, and in the neighborhood, always you will get lesser than this value, right? So that is going to be, in that case, it is going to be local maximum.
Okay.
Because it have the maximum. At here, it have the maximum, and locally, it have always minimum value. But at that point, it have maximum, exactly. So in this, the definition behind is around that. In compare of these all, compare with the other values in the neighbor, you are getting the different exactly maximum or minimum. So with if it is the maximum, then it is local maxima. If it is minimum, then it is going to be local minimum. Okay.
Sir,
Okay.
Sir, can you explain the graph once again?
From your background is too much noise is there. Okay, so this is one thing. Now, I just said that, right? You just derivate. So now, and remain to test that. Let's back to our previous problem, the maximum minimum of the area. So we got that at here. This is a point. Okay. So this I want to explain. So what is here? So in this graph, so in this graph we have these. This is a graph, no? So this is, this is the graph we have. So these points are actually, there is a jump and some locally increase. So this is decrease and again increase. So these are the turning, and this is a sharp corner. Okay, these are the local jump, not jump. This is a increment, decrease. Then again here is a yes, a kind of shape. Here is sharp corner. So this is a graph we have. Okay, now at here. So what is the local maxima? So again in the different definition, I will tell you that compare with the other values in the neighborhood. So if you compare other values in the neighborhood with exact this point, okay, so see that it is going to be in compare of this one, it is the maximum highest point in compare of the neighborhood. So that is going to be, so this point is going to be that side the local maxima. Here is a jump, no? So critical point, I now said that where is a, where it happens. So, or in the different way, if you see the tangent at here, you try to draw the tangent is exactly going to be, or slope of the tangent is going to be 0. Or if you try to draw, that line is going to be parallel to x-axis. So at critical point, it is going to be that. Okay, this is one part. If it is not able, the function is not differentiable there, though it is not, you don't know the exact slope, or even slope of the tangent, or even there is no tangent exists. So in that case also we will discuss that it have a local maxima or minima. So as here there is a possibility that it have the local maxima or minima or saddle point. So these three cases could be. So as here there is a sum. So this is a critical point as the reason of function is not differentiable. And if you see that this is a, so this point, what I said, this point is not, okay, just a minute, this is decreasing. Okay, so just a minute, this is decreasing. Okay, it is local maximum. So from a fixed point, it started increasing. So yeah, so this is a local maximum because as the reason is from corresponding point here, like after this fixed point, before this point is in decreasing, after fixed point, it started increasing. So this point is local minima.
Sir, I don't understand this.
Sorry?
I'm not able to understand this, sir.
Yeah, so let me repeat again. So this is local minima. I said this is a local maxima. So here is, this is a local maxima.
Sir, usually
But this is a local minima, sorry.
No, usually the local maxima and minima are defined only for the open intervals. So why are we considering the endpoints, sir?
So here is not, I'm not considering the endpoint. That's why I open. I made this out.
No, then they should not, it is discontinuous at that point, right, sir?
So it is discontinuous. Please all of you mute yourself. So here is, at least in this interval, we can talk about, no?
Which interval, sir?
So in this interval A to B.
Yeah, in A to B, it is piecewise continuous in that interval.
Yes.
So at the end point, usually we don't, for considering local maxima and minima, we don't include the endpoints, sir.
Yes. So yeah, that's why I made here in this interval, open interval A to B. Previously I made close, but now While talking the open the global, I said let's make it open. So in this open interval we are talking. So in this open interval, this point is in between A to B, right? So we can talk about here is what is going to be. So this point is local maxima or minima?
Which point, sir?
Here, where is the break point?
The break, sir. I'm not able to understand that idea because it is an end point of the of
So
that.
it is not end point. No? Why you are considering with the end point? It is not end point. It is between the interval A to B.
It is not continuous, so we cannot consider that point.
Why we cannot? This is if it is not continuous, then means not differentiable. That means it is not. It is a critical point. So this
Yeah,
is
it
a
is. Yeah,
critical point.
it is not differentiable. So
It is a critical point.
yeah, it is a critical point. It is not
That's why,
differentiable. That I am able to understand. But for local maxima and minima, can we consider that point?
yes, why not? It is if it is a critical point, so that's why I said no. If it is a critical point, then there is three possibility. It could be local maxima, local minima, or saddle. These things could be possible if it is a critical point.
Okay, sir. Now I understand.
Okay, if it is a point is a critical point, then there is a three condition it could have. Either it could have saddle, okay. Either it could be local minima, either it could be local maxima.
It can also be endpoint or not differentiable, right, sir?
Are not differentiable.
Okay.
So here it is. So in that sense, so local minima means, so I said this is a local maxima. No, this is not local maxima. So this is a local maxima. This is a local minima. Why it is so? This is a local minima. Why it is so? So in that sense, it is. If you let's take an interval, okay. Let's take an interval of around that. So it is going to be like this. So this is going to be the small interval. So in that interval, it is decreasing. And there is a point which is not touching here from here, but from there there is a turn is there, no? Decreasing, and from fixed point it started increasing.
Okay.
So that's why here it is going to be, it's look like there is a local maxima, but not, it is not local maxima. It is decreasing, jump is break is there, and then it started increasing. So in that sense, you can always think that it is going to be saddle or local minima or local maxima. So this is going to be local minima.
Okay, sir.
So let's fix this definition. This is the actually meaning of saying to be locally what is happening. From fixed, it is turning. From a fixed point, it is exactly will take a turn, that decreasing, and at sudden it started increasing. And where it is started at sudden, it is going to be, that is going to be your local maxima, minima, or saddle. Sorry. So for the local maxima, decreasing, at sudden it started increasing, means it is going to be local minima. Started increasing, and at the sudden started decreasing. So this is going to be local maxima. While making, you can always you can think like let's make an interval and then think. So here is, if you see that it is a S kind of shape is there. So it is increasing. There is a slightly fluctuation, and again continuing to increasing. Okay. And if you see that tangent is also like it's fluctuation is there. There is, if you try to try to see the tangent, it is going to be, if you try to draw that, it is going to be parallel to axis. So in that sense, you can tell that it is going to be a saddle point. With the graph, while looking the graph, you can tell that. So these are the possibilities for a critical point. Now let's back to our continuing tag, that if it is a differentiable, no. So this test or whatever we are doing here, it is a case for differentiability only. So as we know that we find the derivative, first derivative, and find a critical point. So to find a critical point, we first derivate that and equate to 0 and find the value. We'll try to find the values of x. Once we find that, those points will say a critical points. And there is another point where function is not differentiable, we include that. If it is not, then where the function have only zeros, derivative function have zeros, those point is going to be critical point. So here is only one critical point, this function. So now what we can do, so we'll check with the second derivative test. Now will help you. So let's find the second derivative. So for this function, the second derivative is going to be minus 2. Okay, minus 2. So what is the second derivative test says that? Okay, so here is, let's substitute here value in the second derivative, which is 5 pi by 2. So it is no second derivative exactly constant, which is minus 2. Again you will get here the same value, and this value is going to be lesser than that, lesser than 0. So that means if where the critical point is there, okay, where the, suppose A is a critical point, okay, and second derivative at A is greater than 0, then A is actually local minima. And if second derivative is less than 0, and then it is a local maxima. Two cases we have, and if it is second derivative is 0, exactly equal to 0, then we'll use the different method as the x cube you have. If you think x cube, so for the x cube you add, so critical point is going to be 0. If you derivate that, this is going to be 2x square equate to 0, which is x is equal to 0. So 0 is a critical point. Again derivate that, this is going to be 4. Sorry, this is going to be 3x square. Again derivate that, this is going to be 6x. And at 0, it is going to be 0. So second derivative is not actually passing here. So at here we need the further analysis. We have to locally, we have to see that it is going, how it behaving. So we'll not going to consider this one, okay, at exactly equal to 0. But if it is less than 0, then local maximum at that point is going to be. If it is greater than 0, then it have local minimum. So at here we can see that at 5 by 2, even for all points, it is going to be always lesser than 0. So at 5 pi by 2, it is going to be the maximum value. So maximum area, now we can, you can give x is equal to 5 pi by 2, or even, you can say that x is equal to 5 pi by 2. And now you can use to find the value of y, and that is going to be width and length of the rectangle. So this is all about the critical point. We are done with the critical point, local maxima and minima. Okay. Now let's move to the integration. I think integration part is here, no?
Yes, sir.
Yes, sir.
Okay, so to find the integration, what is the integration? Or even area of the curve, or in the area under the curve. So first thing that, as if you have function fx is equal to x square, if you derivate this function, this is going to be 2x. Okay, this is going to be 2x. So in the different word, what we can say, this 2x, okay, the antiderivative of this 2x is what? Antiderivative means reverse form of this. Antiderivative of 2x is what? Is x square. Means if you integrate this 2x, or even if you differentiate this x square, you will get exactly 2x. So this whatever in the difference, like antiderivative. Now I'm asking antiderivative of x cube. What is the antiderivative of x cube? What is the antiderivative? We'll try to find a such function so that if we differentiate that, we exactly will get this one. So suppose I'm saying this is the antiderivative. Okay, so if you differentiate this function, this is going to be 1 by 4 times 4x cube. So x cube you will get. So antiderivative of this one is x to the power 4 by 4. Okay, so this is one word to saying to be antiderivative. Okay, so this is one thing. It is saying to be, so this is our difference. Say this is integration of dx is going to be x to the power 4 upon 4. So some formulas we'll see later. But there is, another thing is that Riemann sum. So this is the sense. This is for the generally, the derivative and what is going to be antiderivative. Okay, that is one part. Okay, but suppose there is a concept that area under the curve. Suppose you have a curve, no, like this. Okay, in this interval a to b. Suppose you have a function f(x), the graph of the function is like this. So in this interval a to b, what is going to be the area? How we'll get this area? What is this area? How we'll find this area? So for that, for this one, there is no Riemann sum is there. What is the Riemann sum? We'll discuss that. Okay. So to find the area, okay, I'm making like this. This is A and this is B. Okay. This is A and this is B. So, we have the fixed shape, right? If you have a square or if you have rectangle of this width and this length. So we know the formula that it is going to be area is going to be xy. If you have a circle kind of thing, so this is going to be pi x square. Or if you have trapezium, if you have trapezium, so we have some formula. I don't know what is that formula. Some trapezium. So some fixed structure or some fixed figure we have, we'll get that. But this is not fixed. This is a or even let's bend more like this. Now we'll try to find in this interval the area. So this is not a fixed shape. So how we'll get this area? So to find this area, so how to find this area under this curve, like what is going to be this area? So to find that, what we can do, we'll try to break this area. So this is the whole area we have. So what we can do, we'll try to break this area in some part. Okay. Okay. I just break this area, the whole area in the different part. Okay. Suppose this is the interval we have. Okay. Okay, I did this. So this is the interval we have A to B. Okay, this is the interval we have, and we will try to find this interval. What is going to be this area? So this is called area under the curve. Okay. So I just break this one. Okay, I just break this off. So can you tell me what I am doing here with the corresponding to this interval?
Like we have to find the area between these intervals.
So with corresponding to this interval, what I am doing?
In this particular interval A to B, you are finding the area.
Area under the curve, that's fine. What I am doing, I am just breaking this interval in, these are in the some parts. Okay.
Yeah. Yes.
I'm breaking this, this interval in some part. Okay. I just break this. So this is called the partition. If you know, if you remember that this is called partition of the interval. So this is whatever I am just why the purpose why we know now. I hope you that why we sir is doing the partition of an interval means, but because of this purpose that we are actually breaking in some part. So I'm just now naming that. So what I'm naming that, let's say this is x0 is exactly a. Okay. Now x1 is I'm saying this one, this is x2, this is x3, this is x4, this is x5, this is x6, yes, x7, x8, x9, x10, x11, this is x12, this is x13, this is x14, and let's say this is exactly at B, x15 is there. So how many parts, how many intervals are there in small intervals? I just break this one. How many intervals are there?
15.
15 intervals.
15 intervals. Okay. One. Okay. This is 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 intervals. We break our interval A to B in the 15 parts. So this is a partition. This is a particular partition that I just break this interval in the 15 part. Similarly, I can break this interval in the many parts, like more than 15 parts, 16, 17, 18, in many parts. Suppose I'm just breaking this interval again, the same structure. Okay. This is A to B. In only some fixed part. In this part only. So this is x0, this is x1, this is x2, x3, x4, and this is x5.
So like
So
why
this is in the 5 parts.
Breaking it into parts. I'm just asking.
Yes, only just I'm discussing a partition only.
Okay.
Huh?
Okay.
So I'm just discussing only nothing more. I'm just discussing the partition. What is the partition? I mean to say. So only I'm talking about the partition. Slowly back to the Riemann sum. Okay. First we need to know the what is the partition.
Sir, partition means?
So partition means what I'm doing here. I'm just breaking. So that's we are listening, no? So that is I'm doing. No, I just interval. This interval I just break in the 5 parts. These are the parts. Similarly, this one I divided this interval into how many parts? 15 parts.
Sir, just like interval A to B and the partition of this curve.
Yeah, this is the definition. As you know, if you have seen that lecture, then what is that? Partition is what? I'm just breaking that. I'm just breaking in the different parts. So for the same interval A to B, sometime I did 5 parts. Sometime I did here 15 parts. Let's say I'm doing some, again the same structure is there. Okay, but what I am doing, I am very fine. These are very close. I don't know how many, but let's say assume this is of 100. So same interval A to B, I just divided in the 100 parts.
Okay.
So these are the generally called partition. So for one interval, you can do infinitely many ways. You can do partition infinitely many ways. Okay.
Okay, sir. Yes.
And norm is there of the partition, no? So there is one word, norm. What is the norm? Norm is what? So see that this is this is a regular partition I'm doing. What is that regular means? Regular means width of the each partition. This is the width of the each partition. Is actually a fixed number. Means if you see that there is a gap, more gap is looking, assume that these are the regular, means the gaps are actually same for each one. Okay. So this is a regular partition I'm doing. Means each interval length, like let's say I'm saying, suppose 3 to 8, I have an interval. Okay, 3 to 8. What I did, I break this interval in 5 parts. Means what are the parts we have? 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. Okay. There are 5 parts. I divided this 5 3 2 interval in 5 parts. And what is the each? This is a regular partition I am doing. So what is the n parts? Means 5 parts I did. I divided. Now if you think this is 3 and 8, so let me break it here again. Okay, so the same is there. So here is suppose 3 is there, and here is 8. So in 5 part I did. In the 5 regular part I did, and width of each is what? What is going to be width of each interval part?
1.
1. Right? This is 1. So that the width of this regular is called norm. Norm of this is one partition, no? This is one partition. So norm of this partition. Norm of this partition is, suppose same interval 3 to 8. Okay. Same interval 3 to 8. I divide it into 10 part. So now can you tell me what is going to be the norm of this partition? 10 part, 10 regular. Means 10 regular is there. I will tell you the different word also with the norm. What is going to be is 10 regular part. Means regular means each have equal width. So what is going to be the norm of this partition? In 10 parts I divided. This is the same interval.
0.5.
Yeah, so this is how we can get this. You will take the in point. This is, suppose this is B, this is A. So do the B minus A and divide with the number of parts, which is going to be 8 minus 5 upon 10, which is going to be 3 by 10. So norm of each part is going to be, sorry, 3, 8, no? Oh, so 3, 8. So this is going to be 5. So this is 1 by 2. So norm of each, so norm of the party, not each party, norm of this partition is going to be 1 by 2. And can you tell me what is going to be that intervals? 10 intervals. What is going to be 10 intervals?
3 to 3.5, then
3 to
3.5 to 4,
3.5, then
3.5 to 4,
4,
4 to
4 to
4.5.
4.5, 4.5 to 5. So like this, 10 interval will go. So this is one partition. This is one partition of the interval 3 to 8. And norm of the partition is 1 by 2. So this is n regular partition, means in 10 regular parts I'm doing 10 regular part. So each have the equal width. Each interval have the equal width. So there is a possibility that suppose I'm dividing like this, 3 to 5 interval, 3 to 8 interval like this, 3 to 5, okay, then 5 to 6, 6 to 7, 7 to 8. So how many partition I did?
If 5 partition.
This is 5. No, this is 3 to 8. How many partition? This one. This
Oh,
one.
sorry, 4.
Yeah,
4.
4.
In 4 part I did. Is this partition is regular?
Yeah, it's regular. It is equally.
No, it is not. No. This
Why?
distance is 2. But these distances are what? 1,
No.
right?
Yeah, got it.
Okay.
These
It has to be the
distances.
exact same value, right?
Yeah, sorry.
Difference should be
It
same. Difference should be same.
So if it is regular, no, so difference is going to be same. But if it is not regular, so it could be anything. Okay. So now let me tell you the definition of norm. What is the norm? Is that norm is what? So norm of this partition is what is going to be? Can you tell me? What is going to be norm of this partition? This is irregular partition, no? This is irregular partition. So what is going to be norm?
I think 2.
So in this case, why you would think that why it is 2?
Because there is difference of 2.
But difference of 1 is also there. So why you are considering 2?
Because we are choosing that particular interval, like 3 and 5. So we will see at
No,
this
so
interval.
there is a definition of that. Whatever you are doing, either partition could be regular or irregular. Okay, it could be regular or irregular. But
Partition is irregular because there is
yeah, there is a gap jump bigger.
yeah
There is a more
there,
jump. More
there
gap
is
is there. So what is the definition of norm? Is that maximum, maximum distance you can, or maximum, what is that? Maximum width of, compare with the all others. Okay, compare with the all other partition, and what is going to be maximum. So compare with the all, whatever these are the partition you have. It means these are the part in how many parts you divided. Compare with that. Please, all of you, mute yourself first. All okay. So okay. Compare with the all and find the maximum. Maximum is 2 with the in compare of all other width. So the norm of the, if you see the definition of norm is whatever the partition in which, if it is regular or irregular, but maximum width of maximum width of the interval is called going to be the norm of the partition. Suppose I am saying another partition. So this is the same interval 3 to 8. Okay, I am doing a different partition 3 to 7, and then 7.2 to 7.3, 7.3 to 7.4. Okay. Like this, I am doing till 7.9 to 8. Okay. So what is the, so this is a partition, no? This is a partition. So what is the norm of this partition? So generally denoted as norm of, like this. Norm of this partition is what? So this is a
4.
partition. In the set form, you can write like this. And norm of the partition is what?
4. 4, sir, I think.
So 4 is going to be. So these are the irregular. Or sometimes let's say 7 point, so 3 to 7 and 7 to 7.5, and now continuing the 7.5 to 7.6, 7.6 to 7.7, and then continuing. So in that case, what is going to be norm?
Same, sir.
Same norm, because the maximum norm is this, here is 4, and here is what? 0.5, but here is 0.1, here is 0.1, here is 0.1. Width is, there are so many different type of width is there, 0.1, 0.5. But what is going to be, we are going to take with the norm term is maximum value. So this is the definition is of the norm. Why I'm explaining, there is no need of it, but we can directly jump to the, we can directly jump to the Riemann, but these terms are there. So I want to remove your fear that what is these terms are actually. Lecture, these terms are there, norms are there, partisans are there, but it will not take much time. Okay, so this is all about the norms and partisans. So for a fix, even this interval, there are infinitely many possible norms, means there are infinitely many partition of the same interval we can do. Okay, so why this needed, why this partition we talking about? So how we generated this, how we reached this one? We reached this partition with this one, breaking the interval. And how breaking this interval? Breaking these areas. Okay, so we only talk about the regular partition. Okay, let's stick to the regular partition. Okay, we only talk about the regular partition. We are not going to talk about the irregular partition. Okay, we only talk about the regular partitions now. So I try to give the flavor of that regular and irregular partition. But let's stick to and let's stick to the regular partition. And whenever we'll try to always do the regular partition. So again, I'm making the same picture here. Okay, A to B. So let's fix to A to B or fixes to 3 to 8. Okay. So this is 3 to 8 means here this side will go. So let's say this is 3 to 8. We have interval. And I did some partition. So regular partition. So let's say I'm saying I did 15. So now let's back to our previous one, and I'm saying that 15 parts I did in 15. So 15 parts I did. So this is partition I'm doing in the 15 parts. So what is going to be norm now? Norm of this partition? Anyone?
1/3.
1/3. It is going to be 8. How will get that? If it is 15 parts, so take the maximum and take the minimum. This one 8 3. Okay. This end point, take the interval. Take the end point of the interval. Find the differences and divide with the number of parts. So which is going to be 5/15, which is 1/3. That means now how it is so. So this is, let's do on here 15 part I did. Okay, in the regular part. I don't know how many part we can do that here, but here let's assume this is a 15 part. So this is x0 over. X0 is what? 3. What is going to be this one? Now regular part, no? I did regular. So what is going to be this one? Which is our x1. What is going to be x1?
4/3.
3 plus 1/3, which is 4/3. What is going to be this one?
5/3.
4/3 plus 1/3, which is this is the distance. No, you'll add exact regular part we are doing regular in the regular part. So this is going to be just add the norm. This is the norm, means generally distance also called. Okay. Norm means nothing but the distance. So I'm adding the same each time same difference. This is going to be 5/3. So this is our x2. Similarly, this is x3. So what is going to be x3? Our 6/3. Now it will continue. Okay. So suppose I am saying this is xi. Okay. I am saying this is xi. So can you tell me what is going to be xi in the term of I? What is going to, we'll try to make it here. Otherwise we don't want also. Or just I'm saying in the general form, can you tell me what is going to be xi?
Xi plus 1/3.
Xi plus 1/3.
Yeah, sir.
No, 3 plus 1 by.
Xi minus 1 plus 1/3, no?
-1, yeah, right, sir.
So what is, but I will ask, what is our xi then? Xi minus 1?
Sir, xi can, at the next term.
So next term, okay, next term, okay, it is continuing. So can we guess this pattern? So that's the meaning here. That's the purpose I want. Can we guess this pattern? What is happening with this pattern? 3, then 4/3, 5/3, 6/3.
We are always subtracting the next term with the previous term. So
let me write here. Okay. So our x0 is 3, x1 is 4/3, x2 is 5/3, x3 is 6/3, x4 is 7/3. So similarly, I'm saying xi. So can you guess the pattern? What is going to be that pattern? If you see the pattern here is, what is happening?
3 plus I/3.
3 plus I/3. This is the thing happening. If you see that here is what? See that this is, if it is x4, no? X4 is what? X4 is 3 plus, or you know, no, nothing. What is the pattern I'm getting that here? This is 1 plus 1/3. This is what? 2, sorry.
1 plus.
No,
Not 1 plus. We will think in the sense of 3 plus 1/3. No? Yeah. So this is 4/3 we got, or how we got? This is not 4/3, no, 9 by.
That is 10/3, right?
Sorry, this is 10/3. Oh God, sorry.
That's what I was actually trying to ask you.
Plus 1/3 is going to be 10/3. And this is going to be, I didn't match it. So this is going to be 10/3 plus 1/3, 11/3. So this is 11/3. Oh, wrongly I made it. So each time this is not, this is 10/3. Oh, so this is 11/3. He said, and I continued that. So this is 12/3. and we'll go. So this is going to be our 12 by 3, and this is 13 by 3. So now can we guess the pattern now? What is happening here? What is this? 3 plus 2 by 3, right? This is what? 3 plus 3 by 3. This is, what is this? 3 plus 4 by 3. If it is x4, 4 by 3. If it is x3, 3 by 3. If it is x2, 2 by 3. So what is going to be for the ith case? 3 plus I by 3, right? This is the pattern we are getting, right? And x15. We don't want, actually, just I'm playing here, that I want to say this is the partition, these are the partition, these are the, points are you have. I mean to say nothing more. I just want to tell you what is the pattern. I want to observe that these, if I'm doing this regular part, so I generally ask that if it is here xi, so what is going to be xi point? Can you tell me what is the xi point is that? So that xi point is nothing but 3 plus I by 3. That's all. Or even this, you can think of the different word, that 3 plus I into I by 3. Sorry, I into 1 by 3. In that sense, it is happening. Why we needed that? Suppose I said in the 100 part, okay? I suppose I am saying divide this interval in 100 part, okay? Okay, and I ask that what is going to be the 15th. So 15th interval is going to be what? Here and here. So this is the 15th interval. So what is going to be the here value and what is going to be the here value in the, if you do the 50 part, sorry 100 part. If you do the 100 part, so what is going to be the 50th point is here?
In the left side, we'll have 49th x49. Right side, we'll have x50.
So how we can that?
100.5 by 100.
5 by 100.
5 by 100.
So the norm is going to be 5 by 100, which is 1 by 20. Okay.
Yeah.
And can we follow the pattern? So if we try to follow the pattern, it is going to be 3 plus what? 50th. I'm asking. This is 50th and this is 50th one.
15 by 20.
15 into 1 by 20. Right? So this is 50 upon 20.
You're talking about 50th point,
And
not 15th.
Sorry?
It is 50th.
Not 15, I said 50th.
Oh, okay.
50th. So 50th is going to be this one. And what is going to be this one? This is 15 is again 3 plus 51 to 1 by 20. This is the pattern is following, no? Same pattern is going to be. If it is 50th or 4th, this is 3 into 4, or if it is ith, no? So I 3 plus I into 1 by 3. This is the norm. It is a multi. So why I am saying this norm is multiplied with the number of ith and 3 is added there. This norm over, see that this norm is there always. So this is the pattern. Why we want this all? So what is the purpose this? So I will now, we are now almost reached to the Riemann. Only one thing. Now if everything is clear, then only nothing is more in the Riemann. Okay, nothing more. What I will do. So now Riemann definition is what? Riemann definition is.
Excuse me, sir.
Okay.
So only one thing. I said when we have partitioned it in 15 parts, then we have concluded that the norm is going to be 3 plus I into 1 by 3, or 3 plus I by 3.
That point is going to be not norm. Norm is 1 by 3.
Sorry, norm is 1 by 3. Sorry, yeah. That interval, that point, yeah. Yes. That point is 3 plus I by 3. When it is 15, we have got an at a conclusion. Okay.
Yes.
So yes. after like you told that if we partition it in 100 parts, then yes. Again, like by using this particular point or this particular interval 3 plus I by 3, we have directly find that particular at any interval we can directly find the point. So like we don't have to like conclude to another type of new formation of the interval point, like
that is, so that's why I'm saying if it is there, then you just see the pattern. That's why I don't know. That's why I was telling that see the pattern, see the starting at least pattern, and using that pattern you can directly reach to here. Okay. So if
like
it
when
is
it is
there is a
15
issue,
points, then only this particular interval can be followed, no
so
sir?
it is always follow if it is a regular, no regular n part. So that's why I said fix in the regular. So regular n parts, if you regular n part you are doing, this behavior will happen always.
Okay. So we will come across mostly regular n parts only.
So we mostly or even will only deal with the regular. Partition, no, if you're more generalized from when we will started the study of the Riemann, no, so that is going to be the different case. But here is just to know what is the integration, how the integration came.
Okay.
In that sense, we
Yes,
try
sir.
to know.
Yeah. Thank you, sir.
So only we'll fix with the regular, and this behavior will happen. Okay. Now we are almost on the Riemann. Okay, what I am doing. Okay, so what is the definition of Riemann? I will just write, and everything will be Riemann. Everything will be clear. So I'm just writing the left Riemann sum. So I will tell you, or even let's forget about left or right. Okay, I'm just writing that. Okay, I am just taking 3 to 8 and 15, whatever 15 parts I did. Okay, and I have also this points also. Okay, so what are the intervals we have? 3 to 10 by 3. This is our first interval, x0 to x1. This is x0, this is x1. Okay, 10 by 3 to what is now next is 11 by 3.
11 by 3.
This is our x1, this is x2. It will be continued to how much? 15. So sorry, this is what? 8. So 8 is, we can think. So 8. So what is going to be the previous, like if it is here is 8 of the last interval, here is 8. So what is going to be here?
23 by 23 by 3.
23 by 3.
Yeah.
Yes, this is going to be 23 by 3. And next is this 8 could be written as 24 by 3. Correct. Like this will reach to. So 8 could be written as, this is our what? X15. This is X14. So these are the interval I did. So let's make it here. Okay, we are the same as here. Okay, so here is not this one. This is 3 and this is 8 and 15 parts we did. Okay, now what I am doing here, I am taking function value at left side, f0 of this interval. Left value of this one means x1. Left value of, so I am making here, that's why I made here xi and xi plus 1. So I am taking the function value at xi, left value. Okay, these are the values. So here is in the last I am taking the left. This is x 23 by 3. All of you mute yourself because some background noise is there. Okay, so these are the function values we have. Okay, now what I am doing here, let's back to figure. Okay, we are stopping it here, and let's back to here. Okay, so this is our 10 by 3. Okay, so see that here observation is what? So see that this is a trapezium is there. No, trapezium structure is there. No, this parallel is there. This is one horizontal line, and this is a what is a slope kind of line is there. This is a trapezium structure. So what we can do? Let's think about. I just added this extra line, and now I made it a rectangle. And I want to find the area of this rectangle. What is the area of this rectangle with this left point? I will take this function value. So this is the function height, no? This is the height of this rectangle. What is the height of this rectangle? Function value at 3. This is height, our height. And what is the width is here? Our norm. What is our width?
1 by 3.
1 by 3.
So we find the whole area of this rectangle. So this extra thing is added. Okay, this extra thing is added here. Let's reach to the next Okay, so again let's make it here. Okay, and with this left function value at 10 by 3, height of the rectangle, and then width is always same. Okay, by this way we can count whole area with some error. So see that we found the area with some error. So this is called left Riemann sum with the 15 regular parts. With the 15 regular part, we found the left Riemann sum. So what is that here? So this is function value at 3 and then width. Function value at 10 by 3 and then width. So what I am adding here? I am just added here all function value at left in the last interval, this one, and width, and summing them. So let's write. So I sum them all. So this is the sum I did all, and this is saying I'm saying this is the left Riemann sum. Okay, I did this Riemann sum in of 15 regular parts. Similarly, if I'm doing for 100, the same way I will take the left and regular. If I'm saying the 10 regular part, find the norm and take the left always of each interval and multiply that and find the sum. So that is the left Riemann sum again, but 100 regular part. Similarly, 2 regular part, 3 regular parts, 1 regular part. Okay. How many parts you can, in how many parts you can do, this is called left Riemann sum. What is the left Riemann sum? Is nothing but the function value and the norm, that is width of each interval. That's why I said the regular part. This is the left Riemann sum. So let's write in the in the standard form. What I am doing here, I am doing in the summation form. What is that? I started from 0 because this is f0, no, and till what is going to be n or n minus 1. How many sums I took? This is n minus 1, no, because here
n minus 1. Yeah.
14 till 14 I took here. So this is going to be now n minus 1, and this is xi. Right? This is xi. And now norm 1 by 3. This is our left Riemann sum. A more notation form is that like this, the width is sometimes, I don't know how, what is the notation, just recall that notation. This is the only thing is happening. So this is left. Suppose in place of left, I took right. So can you tell me in the same summation form I took right? So what is going to be here? Is going to be I started from 0 or I started from 1? I don't know. How can you anybody tell if I'm taking the right one?
I think you have to start from 8.
8 starting from
No, I think you have to start from 3.
Why it is 3? From each time I am taking from here. No, this is, I will suppose I am taking from right side. So what is
okay,
this?
right side. Yeah, sorry.
Right side.
10 by 3, sir. 10 by 3.
So right side means 10 by 3 will go. So in the summation form, can you tell me here? I am taking in the I form. I is equal to 1 to n or n minus 1 will go.
Sir, we will go to n.
N xi, and now the width.
Yeah. Yes, sir.
This will tell you right sum, right? This is the right sum meaning. You can explain that. Now you can write in the, this is what? 10 by 3 to width plus f of, now this right side is what? 11 by 3. 11 by 3. And then width. And like this will go. And the last, what is at 8 you will find, and 1 by 3. Okay, so this is the right sum. And suppose what I am doing in place of left and right, okay? So there are 3 type of sum, all of you have seen: left sum, right sum. Okay.
So these sums are only areas.
These sums are nothing but the
Right?
areas. No, I am summing. This is the
Yeah.
break part. No, I this
Yes, sir.
area of this rectangle, area of this rectangle, and summing
Yeah.
them all.
Okay.
So in place of now, I'm taking, sometime I took left. So this is called left Riemann sum. I took right. This is called right Riemann sum. We can look at the here at in between also, right? Here, middle point of the width. And height of, we'll use height for this middle point of this rectangle, how much this will form. And then we'll find the value. So can you tell me the middle sum? What is the middle sum? F of, we have the interval what? 3 to 10 by 3. This is first interval. 10 by 3 to 11 by 3. This is second interval. Okay. And 11 by 3 to 12 by 3. This is third interval. Like this will go to 23 by 23 by 3 and 24 by, which is our 8. So let's take the middle point of this each interval. Here we are, what we are doing. So let me make it again the figure here. What I am taking the middle point of, this is our 3, this is 10 by 3. So I am taking the middle point. So how we'll get this middle point? What is the middle point here? How we'll get this middle point?
Adding and dividing by 2, I think.
Dividing by 2.
3
Yes, sir.
plus 10 by 3 divided by 2. Okay. So same way, can we do it here? So this is 3 plus 10 by 3 function value divided by, this is middle point and width. Plus, again for the next interval, take the middle point 10 by 3 plus 11 by 3 by 2. Middle point value of the function and then width. This is exactly the area, no? This is the area it is giving. And then till end. This is 23 by 3 plus 24 by 3 divided by 2, function value at there and width. So this is called mid-Riemann sum. Or
so width is
mid-Riemann.
So this width will remain 1 by 3 only.
1 by 3 because n regular part is written in the same part. 15 part we are doing. The different sum we are trying to find. Sometimes right, sometimes left. But because 50 on the 15 we are did here, there is 15 regular part, no? On that yes, we are doing all sum.
So but like we are computing the middle point of the width, which is 1 by 3. And whatever the function is, we are computing the y value and yes, yeah, and then multiplying it by 1 by 3 again. Yes. So like 1 by 3 is the width,
yes, for each time,
the whole
for
width.
Each interval.
Okay.
Whole width means not a whole width, with the same regular width means for each interval. Yeah,
for particular interval, like, but it is not like finding the area previous, like we are finding the area of the rectangle.
It is again the rectangle in this fashion. It is in this fashion now. Sometime it will contain the part, but sometime it will not contain the part. In this fashion, it is happening.
So, sir, the width will also has to be divided by 2 only, sir.
No. Why it is so? I am taking, okay. So here is not, I am till here not taking. This whole width is I am taking, and only the middle point I use to height.
For height, yes, sir.
I will use to height.
Got it.
And this whole thing is for the.
Okay, sir.
This is a good, maybe many of you have this confusion. So this is confusion is, this is a good one. So this width is I will use for the whole rectangle, but this height is I will use for this middle point I will use to get the height. This one.
Got it, sir. Yeah.
This height. The question could be asked you. So let me tell you the question. Different question is that. The question will be, suppose you have a function, okay? So the question will be, find the Riemanns of this function fx, okay? Find the Riemann sum of the function fx on the interval 3 to 5, dividing this interval in 5 parts, 5 regular parts. So what you will do, 5 regular part means 5 minus 3 by 5, which is 2 by 5, means we got our norm. And he said 5 regular parts. So here is the left Riemann sum. Find the left Riemann sum. So now what you will do? Started doing with the divide with the 5 interval. So what is going to be first? The interval is what? First interval is 3, and next is here is what? Sorry, here is the next point is going to be
3 plus 2 by 5.
3 plus 2 by 5.
Similarly, 3 plus 2 by 5, and then what 3 plus
4 by 5.
4 by 5, and next we'll go in the 5 parts you will get here. And he said left Riemann sum, take always for the left values of f of 3, and what is the norm here? 2 by 5.
2 by 5.
Here is what of 3 plus 2 by 5, and then norm of 2 by 5. Each time we'll do and find the sum, find the value of that. So this is the Riemann sum. Is this clear now?
Yeah, sir, it's clear.
Yes, sir.
Yeah.
So when we write it the summation in a summation form, what will come within the brackets?
So for the middle one, no? So for the middle one, it will be like this. So summation I is equal to, how it will go? 0 to n, right?
0 to
It
n
will go
minus
0
1.
to n.
Sir,
Sorry,
it's
no,
not
it will go
0
to
to
0 to
n minus
0
1.
to n. Because we will use the both in point, no? So this is going to be xi plus xi, or even, n minus 1 also will work, and here is I plus 1 we can do like this, and divided by 2, and this way. Yeah, this here will be n minus 1. Whatever the convincing, no, it is coming in your mind how I will keep here n minus 1 or n, and whatever the sum you are writing, write like this, and this is in the summation form.
For the problem that you have done under this, that 3 to 5 interval, how will we write the summation?
3 to 5. This in the summation form, it is going to be I is equal to 0, because I am taking the left one, no? This is our x0, this is our x1, this is x1, this is x2. So I am taking the left one means 3. So that means it will start it from 0 to, now it will go, because always we'll take the left one, here is x minus 1 and here is n. Sorry, x n minus 1, here is n. So it means here is n minus 1. Now it is going to be x of I, and width is 2 by 3.
What about the middle one?
Middle one is
Here.
I is equal to 0 to n minus 1. Okay. Middle one is what? Xi plus xi. The point is here. This one and this one. Xi plus 1 divided by 2. Function value at there. And the 2 by, what is that? 2 by 5.
Okay.
Okay. Is this clear?
Yeah.
Okay. So let me add one more thing. Okay. And I will end the session. One more thing, that why we are doing so. The question is why we are doing so. We didn't reach to our final integration. So let me tell you the sign. This sign is actually what? This integration, the area under the curve 3 to 8 of fx. So see this sign. This sign is what? This is a bigger s, right? This is a big S sign. So integration sign is not come directly or automatically. It is come with the term sum. This sum word is there, no? Sum. So this integration sign is what? Bigger S shape is there. And what is happening here, no? So what is happening? So this sign is fine, okay? The integration. So see, this I did for 15 regular parts. So this all I did for 15 regular part, 100 regular part. Where is that 100 regular part? Some 100 regular part, 15 regular part, 20 regular part. Suppose I will do for infinitely many regular parts. What I mean to say, so let me write the generalized form. Suppose you have a same interval 3 to 8, okay? And I said divide this interval in n regular part. So we can say, right, here n could be 3, 15, 100. So what is going to be norm of each interval, norm of the interval? If suppose I am saying it's depend on n, no? So what is going to be in the case of norm?
It will be a minus b divided by n.
N. So if it is, you said 15 parts, so that means 8 minus 5 by 15. If it is 100 part, then 8 minus 5 by 100. If it is 1000 part, 8 minus 5 by 1000. And take the middle or left or middle, whatever these are middle one or left one, right one will always be the same here. Only this regular thing will change now. This norm will change. For particularly if it is 15, then according to that, if it is 50, according to that, if it is 100, 1000, according to that, you will write here multiplied number. Suppose I said now I am making here n goes to infinite. N goes to infinite. And I said take the always left Riemann sum in the case of n goes to infinite. So what is happening in the picture form? Let's see it here. So here is our 3, sorry, here is our 3 and 8. Okay. I said n goes to infinite case. That means what? You are making the partition, which is you cannot imagine how much close it could be possible. That is you are doing, no? N goes to infinite means that much partition you are doing. Even you cannot imagine how many parts I am doing, because n goes to infinity is very big, very large number. You cannot tell even, it is not fixed. The case of that it is happening. So let's write here. Let's do it here. So what I am doing here, okay, summation I is equal to, so I'm not fixing the n now. So n goes to left Riemann sum I am taking, n goes to I is equal to 0 to n minus 1 f of xi, and if it is 3 to 5, no, so sorry, 3 to 8, no, so what is that? 5 by n, right? Or even in this fashion, 8 minus 3 by n, which is what?
Yes.
5 by 3, sorry, 5 by n. So this is a left Riemann sum, but n is there, it is not fixed. Now you can always change in n part, 100 part, you can just substitute, and this is one formula, you can say this is one formula. But suppose what I am doing here, now I am applying here n goes to infinite, find the sum with the n goes to infinite.
Is it h goes to n goes to infinity, right?
Sorry?
It's n goes to infinity, right?
Yes, n goes to infinity now. So what is
this value is going to be 0, sir, if n goes to infinity?
No, it will not go to 0. That's the thing here. It will not go to 0. It will give what? It will go to directly this sum. This summation sign will change to integration form 3 to 8 fx dx. And whatever you will get here, this will give you this one.
Why it is it is infinity at the top, right?
No. So under 3 to 8 we are doing, no?
Okay. Under 3 to 8, you're talking about n becoming infinity. Okay,
N goes to n part means n goes to whatever the partition you are doing. You cannot imagine that much partition you are doing.
Okay. You're just confused.
Okay. So let's do one problem on this infinite thing. Okay. And
so one more thing, sir. So just asking. So this the whole like this whole value should be always like it has to be positive. Like I'm just asking.
Not necessarily. So here is that's why here is what sine thing. No, sine. If you remember that lecture, no.
Yes.
If you remember that lecture, here is the it should be at least in this, even even it will, if you do the integration here, if you suppose your curve is like this, and in this interview I'll try to find this.
Yes, sir.
So whatever positive or negative you will find, no, function value is depend on that, and it will manage that. So okay, it will automatically manage that.
Okay, sir.
That's why integration sign will happen. So that's why this finally sum is remembering this sum, and integration sign is there, 3 to 8. If it is 3 to 8 is there, and 3 to 8 fx dx. So it will manage that within that. And even no, this sign is what? Negative value. Too much negative values you will get here. Too much negative values you'll get here. But area is always positive, no? So what is the process, no? In the summation form, so that's why there are so many things here will come now. Now you are talking about the something, no? So what you can do, whatever here is the intersection, no? Till here you will find the sum, this one, and always positive value of means making the negative of them in front of like whatever this side in the bracket, and then find the sum. So this will give a area, this will give area, and then finally sum them. This is the process to find.
Yeah, okay.
Okay.
Yeah.
So these all actually managed by this integration. Okay, that's why it is a more generalized form. You can say the integration. So I mean to say here is this term is actually converted with this integration sign. Now you will do and find the area under the curve. So let's do one problem on this here. Okay, what is that? I'm just taking a function fx is equal to x square. Okay, and I'm saying find the Riemann left or find the. Okay, so I said that the question will be find the area under the curve, this one. Okay, using left Riemann sum. Find the area under the curve, this one, in interval. Let's say I'm saying again 3 to 8. Okay, 3 to 8. Let's make it 3 to 8 always. And you can change with the number using the left Riemann sum. Using the left Riemann sum. So it's very easy. It is not tough. Using the left Riemann sum, find the area under the curve. Means as left Riemann sum, okay, as n goes to infinite case, and or even in this word will be changed with the using divide. This word, this whole word could be changed as find the area under the curve after dividing this 3 to 8 interval into n parts where n goes to infinite. Okay, by using left Riemann sum. Means anyhow you have to take the left Riemann sum and divide in the n parts. So it is not tough. It is very easy. Let's do it here very quickly. We can do what I mean to say here. N parts mean it said n parts means 8 minus 3 by n. Means our norm is going to be 5 by n. And it is says that always the left Riemann sum, find the left using the left Riemann sum. So our interval is going to be 3 to 3 plus what? Our each interval is going to be like this, right? 3 plus 5 by n to 3 plus 10 by n, right? In n part it will go, right? These are the n parts. Suppose n part is that. Is it tougher or becoming a complex thing? Is it understandable or not? Am I audible? Okay. The same thing,
Yes,
only the n.
understandable, sir.
It is n was only n is there. If it is 5 part, 3 part, 10 part, 100 part, n will be changed. So n part I said, because why I am saying this I will use this limit thing, and finally I will show you the integration also. Okay.
This
so
is
n part
511 answer is, I think.
I think it will come. So let's do it here with the sum, this one. So this is going to be using the left Riemann sum. The problem it said in the problem it is said that. So this is going to be f of 3 and 5 by n. Okay, f of 3 plus 5 by n into 5 by n. F of, so this is the Riemann sum, no? 3 plus 10 by n into 5 by n. So it will go to continue int. So this is going to be, what is going to be the int one? Function value. What is going to be, that's why I said the int is needed now. What is going to be in the interval left? What is going to be here left one?
Oh.
3 plus in the case of
n minus n minus
By-
n minus 1 by 5.
n minus 1 into 5 by n, right?
Yes, sir.
So 3 plus 5 n minus 1 on n and 5 by n. Okay, so now see that each term have 5 by n. Let's take the common 5 by n. So you have f of 3 plus these terms will come. Okay, so now this is 5 by n, no? This is 5 by n and this is f of 3. So f of 3 is going to be what? 9 plus this is going to be 3 plus 5 by n square, right? Our function is x square. So is that going to be more tougher? Just a minute.
No, when n tends to infinity, then
square is there.
we'll finally take n tends to infinity, no, sir?
So but we have to find some, no? Okay, so let's do it here, no issues. So this is going to be 3 plus 10 by n square will go to here 3 plus 5n minus 1 upon n whole square. This is the sum, no? This is the sum.
Calculation is tougher, yeah. But
so let's do it here. I don't know how it could be. So this is 9 plus, let's break each interval. So 9 plus 25 by n square plus what? 15 to 30 n.
30
Okay.
by n.
And now similarly 9 plus each time will come from each interval.
Oh, yes.
And what the next thing will come? This 10. So it could be changed with the I think. So here is what? 3 plus.
Sir, 30 by n.
So it could be yeah, it could be yes. Here is, so here we can change with the we can think here, that's why I think is needed. 3 plus what? I 5 I by n. In that fashion we can think here. So here is in the middle one you will write like this. So 9 plus 25 I square by n square plus here is 30 I by n will come, and in the last will also will come. Let's see that how much tougher it will be. I don't know. This is 5 by n. Just patiently you have to take. So there are 9 n minus 1 time. So this is n and minus 1 time 9 is there, right? N minus, so these are the n minus 1 sum, right? Or some summation is left sum. If you remember that left sum is from I is equal to sorry n time I is equal to 0 to n minus 1. So this is 9n. There are 9n.
9n, yes, sir, 9n.
Similarly, here is, now we'll think about the 25, no? The 25 I square kind of thing is there. So each time will come like this. So we can what? We can take this 25 I square, mean 25 by n square common, and what will come? 1 square plus 2 square plus 3 square plus like this till n minus 1 square will come. Correct? This that's why I made it like this.
Okay, sir.
That's why I was saying I change in the I form, then it will be easier to do that all. And this third part is 3 by n term will always come. So what is the 3 by n? You will take common, and what will come? 1 plus 2 plus till n minus 1 will come. Right? Now it is look easier. This is the way to do the sum also. Okay. So now this is we have. Now it is easy, this is the square sum and this is direct n minus 1 kind of sum is there. Okay. So let's do it here. This sum is what? 1 square plus 2 square plus n minus 1 square. What is this sum? What is this sum? There is a formula, no? Anybody can tell what is this sum is going to be? If you are squaring them all. If it is not, then surely at the hint it will be given. So I don't know what is going to be this sum. I have to search. I don't know. I have to also search.
Sir, the formula is for 1 square plus 2 square plus 3 square till n square, the formula is n open bracket n plus 1 close bracket open bracket.
And sorry, what is that? N open bracket, okay.
Bracket, n
and
plus 1 close bracket.
Again
open bracket 2n plus 1 close bracket. Whole divided by 6.
6. Yes, this is it. So this is going to be what? Our, in place of n we are taking n minus 1, no? So this is, in place of n we are taking n minus 1. So this is going to be in place of n minus 1 we will write here, and this is n minus 1 plus 1 is there, so this is n will come here, and this is next is what? 2n. So this is 2n, next is in bracket 2n minus 1, okay, plus 1 is there. So that means it is going to be 2n minus 2 plus 1, which is 2n minus 1. So finally we can write like this: 2n minus 1 upon 6. Okay, so this sum is this, nothing but, and this sum is what? 30 by n. This sum is what? n into n plus 1. No? So n minus 1 into n, because till n minus 1 is there, upon n.
Upon
So
2,
this all
2 n by 2 will come also.
Sorry, by 2. Here is by 2. So finally we have 5 by n, okay, into 9n, and 25 by n square. Okay, and this is n minus 1. So, or even n minus 1, 2n minus 1 by 6. And this is 3 by n. And here n you can cancel out. So here is going to be 15n minus 1. Finally, this term is 2, 15 will cancel out. So finally, here is, let's send this n into inside. So this is 5, this is 9, plus this is going to be n cube. So this is 5 by n cube, and okay, n minus 1, 2n minus 1 by 6. And this is what? 15 upon n minus 1 by n. Okay, this is finally we reach the sum. And now we are taking this is the sum, right? This is the sum we have. Where is that? This sum. We find this sum. Now limit we will apply here. N goes to infinite. Okay, if limit we will apply here. Okay, so this is limit will go inside everywhere. And where it will go? This term?
The constant, yeah, completely it will go, right?
So yeah, it will it will go to here only. The constant will be nothing. It will not affect the constant. So this is 25 into what?
Sir, no. Actually, no, sir. Only the n cube term will escape in that.
Yes.
25 into 2 n cube will.
Yes, this is going to be 25 into here. You can know, you can from n, you can take common here from each term. So this is going to be n cube. This is 1 minus 1 upon n. So this could be converted as a n cube. Okay. And this is 1 minus 1 by n. This is 2 minus 1 by n upon 6. And now we will apply it. So this term will go to where 1, this term will go to 1. So finally it will go to this here, 25 into 2 by 6. And where it will go? It will go exactly 1. Sorry, so it will go to 15. This will go 1 and this will go finally 15. So once you take the limit here 5, it will go 5 into 9 plus 25 into 2 by 6 and 15. And this is 3. Right, so this is going to be what? 5 into this is 15. So this is going to be 24 plus this is what? 25 by 3. I don't know. Now this number will come. I don't know. Let's do integration. 3 to 8 of x squared dx. This is x cube by 3 upon 3 to 8. Sorry, limit is going to be 8 to 3. So this is going to be what? 8 cube minus 3 cube by 3 upon 3. So what is the answer here? I don't know. This should be same, okay? Otherwise, we did some error in the other part. These two are same. So 8 cube is what? 64, right?
No, 8 square. Square is 64.
Sorry, 8 is 64, 512, no? 512.
Yes, sir.
This is 9. So, and this is what? This is 502.
Sir, 3 cube is 27.
27, sir. 9. It's not 9, 27, sir.
Sorry, this is 27. This is 27, and this is what?
512 by 3.
How
sir.
much?
485 divided by 3.
485 by 3. And this is how much? This number is this?
161.66666.
Okay, so what is in the simple ratio form? It is, I don't know. So let's do it here. This is 1 and this is 5 into. So this is how much? 24 into 3, 72 plus 25 upon 3. So 5 into this is 7 and this is 9 upon 3. And if you multiply 9, 5, this is 5. This is, yeah, we are correct. Right? 485 will come by 3.
Yes, sir.
So we reached to the correct answer. Slowly. uh, so this is the
But
way
like,
to find it.
okay. Yes. No, like we can find it direct, like it is easy to find
Sir,
by integration.
but
By
sir,
integration. So how the integration came, this is
Yeah.
the reason.
This is the, yeah. Okay. Yes.
sir, but very long process, sir.
This is so see, this is the objective, no? Sometime if it is subjective exam, then surely it could be asked in this session.
But very long,
Yeah.
sir.
Yes.
So this is the way. So either it could be, this is the left you will take, or either could you take the right one. Okay, either you can take right sum, or you can middle sum. All will go to, or in the sense of now it is a sequence. No, all will converge to this integration sum. Either it could be take left, right, or middle. All will converge to this sum.
Any short format, sir?
Short format is integration. There is nothing more.
So can I
I
ask?
hope it is clear, no? What is the meaning integration, Riemann sum, finally integration is there. How the integration come is this because of this reason, integration, Riemann sum.
So
Yes. So this is very nice method. Yeah. Go on.
can I ask that question in activities?
Yes.
Activity 9.4, question numbers.
9.4. Now I hope the Riemann sum is there. I discussed the Riemann sum now. Which question number?
6.
6-1. Okay. This P1, P2, P3. So this is the interval 3 to 7, and partition is this is regular partition or irregular? All three. Can you tell me?
All 3 are regular only, sir.
All three are regular or irregular?
Regular only. The starting.
No, just explain that it is irregular. All only the P2 is regular. Otherwise, all are P1 and P3 are irregular. Just
Okay.
explain that. See that it is started from 4. It is started from 5.
Oh, that is the reason. Okay, I didn't understand that point, sir. I thought everything was regular because it was plus I into some number by n was.
But see the sum here. It is taken from 4, not exactly. See, it started all 3, but it's taken 3. Here is xi and x. This is from 4 and 5. Only the middle one is started from 3.
Okay. Activity 9.5, question number 7, sir.
9.5. Which question number?
Question number 7.
Okay. So see that this is see that 2x square is there, and 0 to 4 the interval, and how many and part is there. So it is asking the width of interval, norm of the interval. So this sign is the width of each interval. No, this triangle sign is there. So this is the width of interval, and norm I said norm is the whole maximum value of the width.
Yes, sir.
It is norm. And now the Riemann sum. So this is the final Riemann sum using the equal expression. Here is what is the x star? X star is telling you about left or right?
Left sum.
This is left one. This is all our left one. Left Riemann sum talking about. And the final sum is asking square thing, no?
So when I was trying to compute the left Riemann sum for the third option, I'm not getting. I'm getting only 4 outside the bracket, sir. I'm not getting 4 raised to the power that they are giving here.
So that will you can check your I think you may making a numerically error. Otherwise, yeah, you can check. I hope
they have substituted the value of x I star in f of x, and then they are finding.
Yes. So here is maybe you are missing with the 2 thing is to multiply is there. Because of that you are missing.
But okay, so we should substitute and then get the function value.
So it is asking not only for square, it is 2x square. So you have each time you have to do 2x square. For you have to find the value for 2x square.
Yeah, the 2 is outside the bracket in the final answer, sir. That is fine. But the 4 cube.
But this Riemann sum will be given here with the okay. Here is the each time 2 is multiplied. I think maybe inside I don't know something is there. You can check. Okay. Only the numeric part. Like otherwise, I will started doing. Then it will be 10.
Yeah, yes, I understand, sir. Sir, okay, I have one. I just started with activity 9.6, sir. The first question itself is so difficult.
9.6.
First question.
This one.
Yeah, for each one we have to do integration by parts, sir.
By parts. This is the purpose. So, and here is what is the meaning here? Here each time, I think you have to do 3 to 4 time. I think hex cube
sir.
is there.
Yeah.
Many times you have to perform, not only one part. Like only one not you have to do because power is increased in the hex cube is there. So
Yes.
many times you have to perform integration by part.
So it is taking so long time for one question itself.
Okay, yeah. This is activity, no? If you have time, you can do that. Okay. If you are understanding, then you can leave, no? If you know that it
I
is
want to
integration by
practice,
part.
sir. I want to practice it.
So you can yourself convert to x square, then do that.
Okay. Sir. Okay. Sir. Thank you.
Okay, that's all for today. So tomorrow is one session, and nothing is remain now. I think in the area on the curve I told you. So next session I think will as a doubt. Almost if anything is remain with the conceptual, I think Pit or Vishal maybe take. So conceptually I told everything. Yes.
In my dashboard, mock 6 is not there.
So mock will be now. No, there is gap in the mocks. Okay, so
No, sir,
there is a
in
gap.
my dashboard it was not there.
Okay, okay in your dashboard. So till now
Yes.
mock 6 is not released. No, now mock 6 will come. Till now it is not released. The next mock
But
is going.
sir, in Arshdeep ma'am dear, in their dashboard it was there, and lot of students got it.
No, till now I didn't set to release the mock 6. Now maybe from Sunday it will come. So mock 6 is not, there is no mock 6. Now maybe from Sunday or Monday it will come mock 6. Okay. There is no mock 6 till now. There is no mock 6 is there. 1, then there is one gap, 2 is gap, then 4 is continuing, 5 maybe either it could be 5 or 6. I am not remember. Yeah, but whatever the naming is there, you can take with that name. There is no, sometimes you may get bit confused that where is the mock 2, where is the mock 5. But whatever the mocks is there, I used to always send an announcement that this mock is going to be okay. What is that? And then that mock will be released. So you'll get the information in the announcement, you will get here, and then mock will be released. Okay. Okay. We'll meet next day. Thank you so much for joining. Okay. If any kind of doubt you have, please ask. The instructor surely will tell. Tomorrow we have one session also. Okay.
Thank you, sir.
Okay.
Thank you, sir.